Thanks, everyone. We gave a great introduction to why you need, or why you would want different kinds of architectures to address different kinds of science questions and engineering questions. For several years now, we at Marshall Space Flight Center, in cooperation with the Applied Physics Laboratory, have been tasked with a robotic lunar lander development project funded by both SMD and ESMD for various missions. And so I've given updates on this at several previous conferences as well. So if there's something that you missed at some of those previous conferences that I gloss over, please just ask. So this is just to add on to what Bobby was saying too, is that we have many countries are interested, obviously, in the moon, proving out their new space programs and their new technologies. We're in this era here where we see orbiter. And next we're going to see, hopefully, a lot of these same space agencies start putting landers on the moon. This is something that the US hasn't done since the early 70s. And so there's a whole new generation of people, both within NASA and in industry, who are learning to do this again, but for good reasons. Because I'm a scientist and I'm the project scientist for this project, I have to talk about some of this good science that we can do with landers. Right now we're talking about stationary landers. Just for completeness, we have looked at making these into hoppers, and in terms of roving and things like that, we could carry rovers, but we haven't looked at rovers specifically. But with single stationary landers, there are a lot of high priority science objectives that you can meet, and I'll refer you again to the scientific context of the Exploration of the Moon report for a lot of these objectives. We have put a lot of work into the International Lunar Network mission, or the geophysical lander mission, to determine the composition and structure of the moon's interior. Right now, our existing instruments, or the instruments that are at the highest TRL, require a soft landing. They cannot undergo hard landing, and so that was the impetus for going with a soft lander. Polar volatiles, we really need to go and touch the ice, and so this would be something that would enable in situ characterization of the volatile species in these areas, whether you carry a rover on these or not. Lunar sample return, something that's near and dear to my heart. You do have to land and pick up some rocks, whether you go with a rover or not, pick up some rocks, and then you'd use the same platform and launch something back off to the Earth. And human exploration precursors. LRO was our first shot at that, LRO at L-Cross. But there are some things where you do need to land and touch the surface and sit there for a long time, and possibly even demonstrate things like in situ resource utilization, scooping up the regolith, processing it in situ to understand how to do that on a large scale. So there are many things that are uniquely met by landed lunar missions, and that's the impetus for the project. This is something I don't expect you to read, but I just want to put up here to show you the very top line. So this sort of shows our history. We started back in 2005 with the RLEP project, the Robotic Lunar Exploration Program, that turned into the Lunar Precursor Robotics Program, that turned into the International Lunar Network, and that all got wrapped up in this Robotic Lunar Lander Development Project. And we've gone through many incarnations of these, depending on who the customer was, what the requirements were, what the current budget requirements were. And so we've got a lot of changing design requirements and a lot of experience now working through all of these with different objectives, but all from more or less a common core lander design. Even though they may not look like it, they all come from the same kind of design. Right now, because we don't have a specific mission that we're tasked to do, we're just tasked to develop lunar landers and develop the technologies that will get NASA more experience with these, is we've taken an approach that's validation of a lot of our parts, processes, and algorithms through prototype and testing. And so that's what I want to spend the balance of the talk talking about. These are things that we've done sort of in the last year or so that go beyond paper studies and PowerPoint studies of designs and take us into testing hardware and testing algorithms and testing our teams and processes. So we go from our flight designs that some of you have seen now for many years, me presenting here. What we've done is we take all our subsystems. They all have specific risk reduction tasks. I'll show you some of those, in particular in lander stability and propulsion thrusters, and in I'll show you one in GNC as well. And then in parallel, we have these lander test beds or prototypes. And we don't like to call them, they're not particular prototypes, they're not flight-like, but what they are platforms, as Bobby said, that cancel out Earth gravity, get you into lunar gravity environment, give you some time to test particularly the descent phase, the last minute of descent, which is kind of the thing we have the least experience with. Okay, so for GNC, we've with APL as the lead on this. APL has been doing some work with all-HAT, autonomous landing, hazard avoidance and detection, and we have given them some requirements for the landed phase of robotic lander. They get some requirements from the human missions as well. But we said, okay, well, if this is sort of our descent profile, how can we use these algorithms that you've developed for human landings to improve our capability to land on the lunar surface in a very short time scale relative to the human trajectories. These are direct descent, and they're very short time scales. So they've taken some of their algorithms out and their detectors in a helicopter, and I don't pretend to understand all of this, but we did a whole bunch of flight profiles and tested out these algorithms with the processors that would be doing these descent phases. I again didn't want to show a movie as well, but here is a series of stills from a movie which shows lander stability. We built a little model of the lander with the legs that we would be using, and this is something, Adams models are used throughout the industry, and so we just wanted to validate what they were showing us with our flight design and our leg spread, and so we built this little model, and you can see it coming down. It's got some lateral velocity. We don't take that all out, and to see whether it tips over and wonder what conditions it tips over. And hopefully it won't tip over. I think the thing that we are most proud of is our DACS thrusters tests. In designing these landers, we were initially given guidance to make them very small, to make them as small as possible, coffee table size landers that still accomplish decadal survey science. And so we looked at some other places where we might get some technology inputs. One of the places we looked was from Missile Defense Agency. These are divert attitude control thrusters. So these are what guide ballistic missiles. They're designed for very short pulses for a very short period of time, and we want to use them as descent thrusters. And so that means leaving them on for a long time. They're going to get very hot. The performance data was not available from the MDA. That was not something they would share. And so we had to go get our own performance data, which we did. And they do successfully do our flight profile like we want to without overheating. We did continuous thrusting for 66 seconds or 25 seconds on the ACS. So we have a couple more tests to do, but we've got some good data on these as well. So the next two things I'm going to show you are our test beds. We have two of them now. We did one with cold gas, which is just compressed air. We started this in September 2009. It gives us about 10 seconds of flight time. So we can lift off or we can drop from somewhere high up. It's in a net. It can descend, ascend, hover, translate, rotate, anything you want it to do. The innovations in these test beds are that there's no human in the loop. These are all autonomous. So you program in your desired flight profile and hit go, and it's all onboard processing. It understands where it is, what it should be doing. You can do things like say, please hover until you're at 90% of your propellant is gone, and then please descend in this way, and it will do it. So we have over 150 successful flights, and counting on that one. And now I don't remember how to get out of this. Command tab. Command tab. Oh. Okay. Oh, fantastic. So this is what I want to show you. Here's a drop test of that cold gas test lander.
3, 2, 1.
There you go. It's not a very exciting test, but it just shows you the capability. Now it's got a central gravity canceling thruster, and then the rest is all its attitude control thrusters on a pre-programmed, like I said, no human in the loop trajectory there. Right, keep going. That 10 seconds of flight time is great. It showed us we could get this going, we could do this, but it's not enough to really test all our software, all our algorithms. And so we need something that's going to give us a minute or more of flight time and descent time. And so we went with something that looks a little more flight-like, has a little more mature design. This is hydrogen peroxide. So it gives us a little more than a minute of descent time. Again, it's got your thrusters in their flight configuration. It's got a gravity canceling thruster in the middle. It's got more flight-like detectors and sensors on it. And it has our ground control software that we would intend to use for flight. It uses Core Flight Executive. And so this is sort of the next generation. And now I'll show you quick time. So I want to show you, this is a movie of its flight, if I can get it to come up. Here? Oh yeah, okay. Oh no, that's the wrong one. Come back up. How about this one?
We'll confirm go, no go for test. Operations engineer.
Go.
Flight software.
Go.
AE.
Go.
Data. Go. Command.
Go.
Systems engineering is go. RCL.
Go.
System safety.
Go.
Test director.
Go.
Test conductor is go.
Prop ISO valve is open. Thruster speed pressure is 715 psi. All propulsion system pressures and temperatures are within limits.
You can see it going to infrared here because it's hydrogen peroxide. It'll get pretty steamy in there, so that's why it moves to IR.
UCV is nav ready. Countdown. 2, 1, nominal. Vehicle is ascending. Vehicle is hovering. FET 15. FET 20.
There's that gravity canceling thruster, and then you can see these pulse thrusters firing to maintain its attitude.
25. Altitude 2 meters.
Lateral is good.
FET 30. FET 35. Vehicle descending.
So it was a 36-second flight. We have plans to take this out. It has progressed beyond that flight. That was one of its test flights, and we are going to take it out and actually drop it from 30 meters and hope for the best. But like I said, we do a lot of testing, and the thing that makes both of these test beds different from other test beds that you see is this is no human in the loop. This is pre-programmed flight. It goes and it does its own thing like it would do in flight. So the takeaway is that we've developed several lander concepts encompassing a large range of mission types, different kinds of payloads that you could put on them, and these are pretty mature lander design concepts, but we want to take it beyond that and really start implementing some of these ideas. And so we have these test beds. These test beds, we want to work with you. If you have things that you want to fly on these test beds, industry, academia, other government centers, please come talk to me and I'll put you in touch with our team. Thanks.
Any questions?
Do you think you could briefly explain what a warm gas peroxide thruster is?
Well, the propellant, instead of being compressed air, is hydrogen peroxide. So it just gives you a longer flight time.
Or no catalyst bed?
No, well, you know what, I don't know. I'm sorry, I don't know. Yeah, something I probably should know.
What kind of payloads were you looking at for those?
Well, we are not developing any payloads. What we do is we work with the customer, either SMD or ESMD, to define notional payloads that then we can size the lander or size the the propulsion system or whatever to accomplish that kind of mission. But we are not developing payloads.
Any more questions? I think that's it. Oh, we've got one more.
I was just wondering if you're sharing any of the results of your work, say with regard to software or sensors or anything like that, with the, say, the Google Lunar X Prize teams or anybody else in industry.
Yeah, when we are approached by industry, we will work with industry. Now, whether we will just give the data away, probably not. It's something that we want to... I don't think so. I think we're looking to partner more and to use this experience to partner. But that's a little bit above me. I can talk to you more about that if you want.
Okay. Thank you, Barbara.